In this video, I will discuss about the transformer low voltage side, secondary low voltage side, cable selection. Generally, it is through bus duct. This transformer secondary side, due to the higher current because of the low voltage, this current will be higher, and depending on that current rating, this low voltage cable size, number of runs, and size also will be higher as compared to this high voltage side. Suppose this is high voltage switch gear or the medium voltage switch gear, and from there this is stepped down, this voltage is stepped down through a distribution LV distribution transformer, and this is 415 volt or 400 volt LV side. So you can consider this high voltage side cable size will be single core, will be single run 3 120 square mm or 3 core 240 square mm, depending on the transformer rating. But the transformer secondary side, this LV side, this current rating will be higher, and we need to select higher size of cable along with the uh, number of cable runs. That will be more in case of secondary. So if there is no bus duct connection from transformer secondary up to this area or PMCC, we need to consider the low voltage cables. So today we will discuss about this portion, the LV cable connection in between distribution transformer secondary and this LV PMC or PCC. So let's go to this spreadsheet. Here this is the sample calculation from 2.5 MVA transformer. As you can see, this is rated reactive power 2500 kVA. So this transformer rating is 2500 kVA, and this is 400, this is 415 volt LV switch gear or LV PMC or PCC. So before proceeding, we need to discuss the basic things, whatever the criteria for the selection of low voltage cables. Number one is the short circuit criteria. So here this transformer rating is 2500 kVA, and obviously this will be connected here through circuit breaker. So this incoming circuit breaker will be provided, that will be part of this LV board, and here this is breaker operated. That means we need to check the short circuit criteria as well. So to check the short circuit criteria, so this is the equation: A equals to I is the short circuit current into root T by K. Here short circuit rating ISC, this is 50 kiloampere in this LV board I've considered. In some cases it may be 65 kiloampere or 100 kiloampere or 80 kiloampere also. And this T is, this is on circuit breaker fault clearing time. Suppose this is considered here 0.3 second, and K, so this is 50 kiloampere for this T is 0.3 second, and K is the K is the factor. Here this is 0.143 for copper XLP cable. This is as per IEC standard 60502. So this is for copper material, and if it is aluminum cable, then this value will be different. And using this formula, we can calculate here the minimum cross section of the conductor as 191.5 square mm. And okay, we have considered here 630 square mm based on other criteria. So that thing we will check now, but this is the minimum requirement. This must be 192 square mm minimum cross section to meet this short circuit criteria. So this is number one. Number two is the continuous current rating criteria. So to continuous current rating, since this transformer rating is 2500 kVA and secondary side is 400 volt, full load current 415 volt, this is the 415 volt LV bus, and this is the continuous current it is calculated. So 2500 kVA divided by root 3 into LP voltage, so this is coming 3608 ampere. Now cable selection based on the continuous current carrying capacity, we need to check here the overall derating factor. So this overall derating factor here we have considered 0.6. so this overall derating factor is the multiplication of individual derating factors. That means this depends based on the cable laying, cable installation, uh, and cable. Next factor is the temperature correction factor, and how it is going. How it is laid. Suppose it is in trefoil formation, or it is single layer or double layer. So based on this installation parameters and temperature correction factors, so this derating factor must be applied. So the standard ampacity of this 630 square mm cable we cannot consider, because there must be some derating factors. So here we will be derating this full load ampacity of this cable, multiplying by this overall derating factor 0.6. Okay, now ampacity of cable in air. So this is 1027. This is from the cable manufacturers catalog. Yep, obtained this value 1027 ampere. And now what will be the next derated ampacity in case of air? So this will be 1027 multiplied by 0.6. So this derated value is coming 616.2 ampere. So we have to consider this derated ampacity of the cable, not the rated ampacity of the cable. So we'll be considering this 616.2 ampere here. Therefore the number of cable runs per phase required is that full load current FLC divided by this derated rating 616.2. so it is coming 5.85. that means round figure 6. Hence the cable size selected based on the continuous current rating is 6 runs of single core 630 square mm copper XLPE. So we have proposed the cable size as single core 630. So based on this, from the cable manufacturers catalog, we have obtained this cable ampacity in air, and this is multiplied by overall derating factor, and this is the derated ampacity of cable. So based on this we have calculated the number of run required is 6. So the cable size is selected 6 runs single core 630 square mm copper XLPE cable 0.6 by 1 kV grade. Now the third criteria is the voltage drop criteria. Voltage drop criteria we need to check. There are two options. There are two sub criteria actually. This is the voltage drop criteria under running condition and voltage drop criteria during starting condition. So this is during running condition. So during running condition, generally this is 3%. 3%. Here I have considered 2.5% because this was the project requirement. So we need to limit this uh, running running voltage drop to 2.5%. So we have seen in the continuous current rating criteria, the number of runs selected is 6. So here we need to check the steady state voltage drop at the 415 volt bus considering number of cable runs. So here this is the formula root 3 into I means maximum running load current into R cos phi plus X sin phi. R is the approximate resistance of cable in ohm per kilometer at 90 degree centigrade. Here you can see, and X is the reactance of cable in ohm per km. So this data will come from the cable manufacturer's catalog into L divided by N into 1000. So this L is the length of cable and N, capital N, is the number of cable runs. Using this formula we can calculate this voltage drop during running condition as 0.83 volt, and we have converted here in percentage drop. So this is coming 0.21%, which is less than the allowable voltage drop 2.5%. so this is less than that. So here we can say, okay, you can see this is the 3608, this is the running maximum running load condition. Here is the R value of R, value of X. 60 meter we have considered. You can change this cable length also, and here number of cable run, and cos phi. Load power factor is considered as 0.8. So from this calculation we can say that the steady state voltage drop is within the limit 2.5%. Hence the proposed cable size, whatever selected, 6 runs of single core 630 square mm copper XLPE, it is safe. Now we will check the voltage drop criteria during starting condition. Here the allowable voltage drop during motor starting is 15%. Actually this is particularly applicable for the motor feeder. Suppose this is the 350 kilowatt motor, and during running what will be the voltage drop, so it is considered here. So we will not check this starting voltage drop for this particular feeder from transformer secondary to LV side. So basically what we have considered here, this is the continuous, based on the continuous current rating in from the transformer secondary up to the LV board. And number 2 is the short circuit criteria. From short circuit criteria we have seen this cable size is sufficient, and also the running voltage drop, this is also within allowable limit. So in this way we can select, or we can cross check the cable size in case of transformer secondary outgoing, or for the incomer cable from the incomer for the incomer cables from transformer secondary to LP PMC BCC incomer cable.